Hello everyone. In this video, we are going to talk about centroids, or you might call them center of mass, center of area, center of curve, and so on. So we want to learn all we need to know about this important topic. But before we start looking into formulas and examples, the first question that we need to answer is, why are they any important? Why should we learn them in the first place? And the answer is they are appearing in lots of different places in engineering and real world examples. So, for instance, let's say if you want to balance an object, right? If you want to balance an object, let's say it's a beam or slender bar, anything, and you want to balance it, the place that you have to balance it should be right at the centroid, correct? So if you play the seesaw, you know that. So here is this beam, and then there is a support point, something like there. And then if these two people, assuming that this is like exactly in the middle of it, right? If these two people that are sitting here, they have the same weight, of course, it is going to be balanced, and this bar or beam is going to be flat or horizontal. If one of them is heavier, then the center of mass of these two objects and the beam will move a little bit to the left of the support point. So the centroid is going to be here, and that centroid will create a moment about the support point O, and that will cause the rotation. So that is a simple case, but in more advanced cases, you might say, like, where? Well, for instance, let's say you have a dam, right? So you're designing a dam, and this is like the cross section of it, and then you have the water here. And when you go down in depth of water, the pressure of the water increases linearly with depth. So while the pressure here is small, as you go down, it gets bigger and bigger. And if you want to find basically the point that is like the centroid of this distributed load, correct? You want to replace all of that distributed load with a single load. You want to do some analysis. You want to find reactions and everything. So in any system with a distributed load, what you need to do is you have to find the area under the curve that is the equivalent force, but where would you put it, right? So let's say the force that is like, this is a triangle, and the triangle, area is the height times the base time divided by 2. But where would you put it? That's where the centroid comes in and says, for instance, 2/3 from the vertex and 1/3 from the base, right? So you put that equivalent force right here. Or even better, more advanced, if you look at the leg robots, if a leg robot is walking or moving, and you want to look at the static stability of it, by that I mean like whether that robot is going to fall down or not. So let's say it has 3 legs or 6 legs or anything. So let's just say it's 6 legs. So if these are the contact points of these 6 legs of the robot, then when you connect them together, you're going to get a convex hole. And if the center of mass of the robot, if you're looking from top to bottom, it's a top view. If the centroid, center of mass of the robot, is inside this polygon, then the robot is statically stable and it's not going to fall down. Otherwise, it is not going to stay on these legs, and it is going to basically collapse on one end or one direction or the other, right? It's going to tilt to the sides. So there are lots and lots of applications when you're looking at profiles and in aerospace engineering, and when you're looking at airplanes and so on. Then you have center of pressure, right? And the location about the center of pressure and the center of mass of the wing and everything. Those are the things you use when you're looking at the stability of the aircraft, and also when you're looking at, for instance, centroid of the entire lift and the entire drag forces, where you want to put them. Again, that's a similar discussion like the dam discussion that we did. So they are really, really important, because you can replace an entire system by a single force at a single point, and the location of that single point is very critical. So the thing is, how do we find them? And here, first, I start with centroid of areas, which is probably more common and you have seen it a lot more. And then I go higher up in dimension, so I go to center of volumes and also to center of lines. So we're going to look at the problem in 2D, 1D, and 3D, right? And so centroid of areas, as I said, are very simple. Now you might say, what does this have to do with center of mass? Well, if the object is flat with a small thickness, right? So let's say this is a slab like this with some very small thickness, then the location of the center of mass of the object and the center of area for the cross section of the object, they are going to be right on the top of each other, right? Except that, of course, if you look at this face of it and the other face that you have on the other side, then the center of mass is going to be in the middle of the thickness, correct? But if you look at them in this side view, they are exactly on the top of each other. So the way you calculate it is the x-coordinate for the centroid of the area is what we call the first moment of the surface with respect to the y-axis divided by the entire area. So that integral of dA over A, that is the entire area, surface area of the object. And this one here is called the first moment of the surface with respect to the y-axis. Now, why y-axis? Because x is the distance of this element dA to the y-axis. That's the distance of it to the y-axis. And remember, moment is like an arm times a force. In this case, is instead of a distance times a force, it's a distance times the area of that element. So we call it moment of area as opposed to moment of a force. So this is the moment of that small dA with respect to the y-axis, integrated over A to get the moment of all of the surface with respect to y-axis, divided by A, and you're going to get x bar. And similarly here, this is the entire, basically, first moment of surface A with respect to the y-axis. Again, because, x-axis. Because y here is the distance of this element to the x-axis. Okay, so you can find these two values or these two coordinates. Now, what does it mean if you find them? So what does that mean physically? It means that instead of having a distributed surface like that, you can literally squeeze the surface. You squeeze all of that surface into a single point. You squeeze that entire surface into a single point and say that that single point has a cross section of A. It has the entire cross section squeezed into it, like a Big Bang, right? Remember, everything is compressed into a small point. Now, where would you put that small point that has a cross section A? You put it at location x bar and y bar. Then, the first moment that this small point with the cross section A has for both x and y axis is going to be the same as the entire surface. Why? Because if I say, what is the moment of this A here with respect to the x-axis? You say, well, the area of this is A, and it is at distance y bar, so this is going to be A times y bar. And for a y-axis, the surface is A, the distance is x bar, so this is going to be ax bar. So either it's equal to ax bar or ay bar for this one on the right. Now for this one on the left, how do you find the first moment for x and y axis? You do it by integration. So this one is the total moment of the actual surface with respect to x-axis. This one is the entire one for the this one for the y-axis, this one for the x-axis. So if you say these two are equal, look, if you say these two are equal and then these two are equal, look, then you see clearly from here that if you divide now both sides of this by A, then x bar is going to be that integral over a. So you get this formula. And similarly here, correct? You say these two are equal, divide both sides by a, and guess what? You get this formula here. So these two formulas are coming from equality of the first moments of the actual surface with respect to x and y axis and the squeezed surface that has the cross section A, but it's at one single point in location x bar and y bar. So these two are equivalent to each other. Okay? So it's clear where these formulas are coming from. Now that we know where these formulas are coming from, it is time to talk about how you perform that integral in the numerator, or also denominator too. So how would you calculate this integral? So for that, we need to consider this differential element dA. What is the kind of shape of dA such that we can move it all over the surface and we integrate it all over A? Okay, so this is the part that we have to talk about. And to show you that, we're going to go through an example to better understand it. So let's say the area I have is limited between line y of equal x and the curve y equal x squared between 0.00 and 1 and 1. So if I have to squeeze this shape, this surface with a single point, and squeeze all of this area into that single point, where should I put that single point? This is y bar, this is x bar. Where do I put this? So I say these two are equivalent to each other, okay? So we have to do that. Now, if you look at the x bar, remember x bar was the integral of x dA over integral of dA, which is the entire area. And they are both over the entire A. Now, if you look here, this dA element is multiplied by its x coordinate. So when I calculate this integral, it's good that if I can consider an infinitesimal element dA such that the x value of it is constant. If the x value is constant all over this element dA, then I can easily I can easily calculate this integral. And you might say, well, look at this element that you have here, this small square. Since this thickness of it is very small, so x is the location of the center of it, or maybe the left side of it, and this thickness from here to here is only dx, and the y thickness of it is dy. So it's very, very small. These are differentials. In limits, they go to 0. So I can say x is roughly the same from the left side to the right side because it's sx and from x to x plus dx, right? In this range, I can say x is roughly the same in this range and y similar. So clearly, since dx is approaching 0, this is almost a constant x and similarly constant y. But when I calculate the x bar, I do not need y of the element to be constant. All I want is x of the element to be constant. Okay, so I can, because moving this, you have to come up with a strategy, as I said, to calculate the integral all over the surface. So you have to move this guy all over the surface, right? Have a strategy to sweep the entire surface with this small infinitesimal element so we can perform that integral. And that's not easy. Okay, so if I have a small square here, how would you move it in both x and y directions so it sweeps the entire surface and can paint? Consider that like the tip of my pen. Okay, how would you move my tip of the pen so that I can what? I can paint the entire surface. That means integration over A. How would you do that? So for x, as I said, instead of going with a small square, I would rather go with what? With something with a fixed x. How does that look like? Well, here we go to a fixed distance x from the origin, and then at that location, I draw my element as a vertical bar like this, which from the top, it's limited to the y equal x line, and from the bottom to the parabola, okay? And the thickness of this small element, I consider it dx. Clearly, the x all over this element is constant because it has very thin thickness in the x direction. The y of it is variable, but the x of it is constant. So I can use this element, this vertical small slender bar, to basically, and all I need to do is to move it left and right. From x of 0 here to x of 1, if I move it, then this small bar is going to sweep the entire surface. So that's what I'm going to do. I say this is equal to integral of x times. Now the question is, what's the area of this guy? So what is dA? What is the area of this small rectangle? Well, if I know this h, the total height of this, so if I call this total h, if I know that h times dx, height times width, is the area of this shape. And you might say, well, that shape is not exactly a rectangle. If you zoom into it, that's how it looks like, huh? It's not a rectangle, you're right, but if this dx is almost at 0, that is going to be so thin that is practically, you can consider it a rectangle. These changes in the heights of these two ends are not considerable. In limits, when dx goes to 0, they are not considerable. So this is what we're going to do, h dx. So here I'm going to write it as h dx. And this is going to be integral of, again, h dx. So wherever I have dA, I replace it with h dx. Now the problem is this h is not constant. This h is variable. If my element is here, you see the height of it is small. If it's here, it's almost 0. When it comes to the middle, it gets bigger, and then as it goes back toward the right side, it shrinks back again to a point and to 0. So this h is actually a function of location, is h of x, right? This h is h of x. But how can I find it? Well, that's not so hard. If I know y of this top point and y of the bottom point, and I subtract them, that's all it has to be. It's the subtraction of y of the top minus y of the bottom. And what is y of the top? Well, y of the top is coming from the line, so at that x point, y is also equal to x. Y of the bottom point is coming from the curve, and y of the curve is x squared. So this point is x squared. And since you are between 0 to 1, x is actually bigger than x squared. So don't be surprised that x is bigger than x squared. It is, because you are between 0 to 1. So this h, as you can see, is the top y, which is x, minus the bottom one, which is x squared. So this h is x minus what? X squared in both places. Done. So now if we continue, this is going to be the integral of this x times x minus x squared. So x times x is x squared. X times x squared is x cubed. And then dx. And the bottom portion is just x minus x squared dx. Now x goes from what to what? Clearly on the left side x is 0, on the right side is 1, so the limits are 0 to 1 for both of them. Let's move on a little bit. And that's all I need to do. So integral of x squared is x cubed over 3, calculated at 1 and 3, that's going to be 1/3. This is going to be minus 1/4. This is going to be 1/2. This is going to be 1/3. So it's going to be 1 over 12 over 1 over 6, and that is going to be what? 1/2. So you see the x of the location of the centroid is 1/2. In the middle exactly. The x of the centroid is actually 1/2 in this case, and it is fine. It is. Now you might say, is the y of it also, y bar of it is 1/2? Well, you'll find that it's not. But you see that x of the centroid is 1/2, so I can squeeze that surface down to a single point at x bar of 1/2, whatever y bar that we're going to find next, and I can put all the area right into that point. So this is for what? This is for x bar. Now let's go to y bar. So how do we calculate y bar? Remember, y bar was integral of y dA over integral of dA. Now, do I need to calculate this integral of dA one more time? No. Why? Because that's just the area. And guess what? The area is already calculated. That was 1/6. So I'm not going to redo this part, okay? This is 1/6. It's already done. All I need is to calculate the top portion. Now, if you look at the top portion, what you care about here is y of that element to be fixed. So here, maybe I can use a different element that has a fixed y, a fixed height, rather than a fixed width. And that should allow me to do this integration simpler. So what I will do this time is I change the shape of my element. How do I do it this time? I'm going to clean this a little bit, if you don't mind. And I pick a y element that has a fixed y. So I go to a fixed y. And then I add an element that has a small thickness of dy. The left side of it is on the line, the right side of it is on the curve. And if I move this element up and down, guess what happens? It is going to sweep the entire surface. So I can use this horizontal element this time, right? So this is going to be integral of y times, that is 1/6. So what is dA? What's the area of this guy? Well, this time I say, if I know this width from the left side to the right side, if this guy is W, then W times dy is going to be the area of that rectangle. Again, that's not a perfect rectangle, but when dy goes to 0, that is going to be a very, very narrow rectangle. So I can use that formula. Good. Now, is this W fixed? No. When you move this up and down, right down here, it is almost 0. And as you get closer to the center, it gets wider and wider. And when you pass it again and go up, it gets thinner and thinner back to a point. So the W here is actually, this W is a W of Y, right? So if I want to clean this up, this is W of Y dy. Now, what kind of function is that? Well, guess what? If I have this x of this left point and x of the right point, and I subtract them, x of right minus x of left, that's all the width of this one is. Now, what is x of the right? X of the right is coming from this curve. What is x here as a function of y? X here is square root y. If you take a square root from both sides, you see x is a square root y. What is the x of the left side as a function of y? It's just y. So it's going to be square root y minus y. And again, between 0 and 1, square root y is bigger than y. So what you will have is square root y minus y, right? That is this w, and then times dy. That's all it is. And y goes between which two limits? Again, this point is 0, 0. That point is 1, 1. So clearly, your y goes from 0 to 1 as well. So this is going to go from 0 to 1. And again, integral of here, this is y to the 3 over 2. So integral of that is going to be 2 over 5y to the 5 over 2. And at 0 and 1 is just that. And then minus, this is y squared, it's going to be y cubed over 3, so it's just going to be 1/3 and over 1/6. So in the numerator, you're going to have 15, and that is a 1, and this is 1/6, and it's going to be 6 over 15, basically. Or if you divide by a 3, it's going to be 2 over 5, or 0.4. right? So y bar is not 0.5, is 0.4, right? 2 over 5. So that is where you should put it, at x of 1/2 and y of 0.4 or 2 over 5. That is where you can squeeze that entire surface into a single point, and you can show it with this symbol. This symbol here is what? The symbol of centroid. Right? If you draw it bigger, so it's like this, and then these two sides are basically painted. Whenever you see this symbol, that's the symbol of centroid. So that's where it goes. Good, done. So this is how we can do it. Now, there is one other thing that you can do to calculate this second integral, if you wanted. You might say, well, if I wanted to calculate this second integral, could I still use that vertical element that you use for x bar? Could I still use that? Well, you can, but it needs a little bit extra thing. What is that? Let me show you. So, can I still use that? Remember, for that, we move to location x, correct? Gave it a thickness dx, and we use that to calculate x bar. Now, the question is, for y bar, how can I use that? So let's take a look. Well, in this case, for this element, y of the element is not fixed. Y of the element is changing from this point, which, remember, it is x squared, to this point, which is x. It is changing, and it's not fixed. So this y is variable. But can I replace that element with its own centroid, right? If it's a small rectangle, as you know, and it's very easy to show, the centroid of any rectangle is exactly in the middle. Okay? You can show that, and we're going to talk about the objects that have symmetry lines. So any object that has, let's talk about it right now. Any object, that's one of the easy things that you can talk about centroid. Any object that has any axis of symmetry, the centroid should fall onto the axis of symmetry. So if you have two axes of symmetry, then clearly the centroid will exactly be at their intersection. Okay? But for instance, if you have, and you'll see, if you have a quarter of a circle, this one has only one, basically, axis of symmetry. And so your centroid should fall on this one. Where? We'll find out. But centroids always fall onto the axis of symmetries if more than one on their intersection. So for a rectangle, it's in the center. So can I consider, instead of this element, can I say I can squeeze that element into a single point where right here in the middle of it, because that's a rectangle. So I can say the dA of this element, I can squeeze it into one point right in the middle of these two y's, the y of the top and the y of the bottom, and I can consider it there. If that's the case, this is going to be integral of. So the y that I have to use for that element is the y average of that element. And what is that? Remember, the top point, y of it is x, the bottom point, so this is y of the top. This point, y of the bottom, is x squared. And this point here, y of this centroid, is the average of y of the top plus y of the bottom over 2, because that's the middle point. So it is going to be x plus x squared over 2. So can I replace that with this guy? If that's the case, this is going to be x plus x squared over 2. That's the y of the centroid. Okay? Yep. And the dA for that element, if you remember, it was x of the top minus x of the bottom times dx. So it was x minus x squared dx, that is dA, and over 1/6. And this integral, of course, remember, goes from 0 to 1. So can I do that? Is that a possibility? Well, let's go find out. So here, this is x plus x squared. That is x minus x squared over 2. So you get a 1/2 if you bring 1/2 out. And this is going to be the first one squared minus the second one squared. So we get this. And if I continue here, this is going to be 1/2 times. This is going to be 1/3. That is going to be 1/5 over 1/6. And this guy here, this is going to be 2 over 15. And if we cancel out these 2's, you get 1 over 15 over 1 over 6, which is 6 over 15. And remember, this is the same as 2 over 5. You divide by 3. And how much was y bar last time we calculated? It was 2 over 5 or 0.4. And you get here the exact same thing. So to calculate y bar, yes, I can use that vertical bar. I don't need to use that horizontal bar. But I have to use the y of the centroid of that rectangle right here. And yes, I can use that element to calculate both of them if I want to. Okay, so that's another thing that I wanted you to learn about the centroids and doing centroids of areas. Now, going forward, sometimes some curves are given such that it's better to do these calculations for x and y of the centroid in polar coordinates rather than the xy coordinates. Why is that? Well, the reason is in the polar coordinates, something about their r or theta is constant or it's more accessible. Well, what do you mean by that? Well, I'll show you. So one example is going to be a quarter circle. I show you if I want to find the quarter circle centroid, it's a lot easier to do it in r theta coordinate rather than xy coordinate. And I'm going to show you in 1 second. But if I want to do that, what is the formula that I have to use for x bar and y bar? Because all I learned was x bar was integral of x dA over dA, and the y bar is similar, y dA over dA. So what do I do? Well, all I need here is to look at the polar coordinates. And what would be the shape of this element? Remember here we use this small square. In this small square, the x is a small thing and dy is a small. So the way we got this element, we moved to position xy, and then in the x direction we incremented a little bit, in the y direction we incremented a little bit, and we got the other corner of it, and then we formed a square. This is how we got this element in rectangular coordinate. In r theta coordinate, however, the coordinates are defined by r and theta. So we come to this point here, which is at angle theta and location r. And then in the r direction, we increase it by dr, and we change the angle theta to theta plus d theta. So from this corner, we go to this corner, and clearly, because you're changing r and theta along arcs, r radially, theta along arc, the shape that you will get is not a perfect square, but it's kind of like a slice of a circle. But since r and theta, dr and d theta are very small, I can say this is approximately a square or rectangle. And what's the area of a rectangle? Well, it's one dimension times the other one. And what is this dimension? Well, since theta is in radians and this is r, the length of the arc in front of d theta with radius r, this is r d theta. So one side is r d theta, the other side is dr. So the area of this guy is going to be r d theta, which is one side of it, times dr. And that's what you can see here. And of course, x is r cosine theta, y is r sine theta. So if we look at the x bar, remember x bar was what? It was integral of x dA. So for x, I replace it with r cosine theta. For dA, I replace it with r dr d theta. And similarly for y, again, this is y, this is dA. And that is just the dA in the denominator. Now, here is a double integrator. Why? Because you're allowing both r and theta to change simultaneously, so it's a double integration. And since everything here is a product, then I can separate this this one double integral into the product of two simple integrals, or basically where one is r, one is theta. Look here. You see, one is just r integral, the other one is theta. The same thing goes for denominator. So you see, I can calculate two simple integrals, one in the r direction, one in the theta direction, multiply together, and that will easily give me x bar and y bar. So doing some of these shapes in the r theta coordinate could be easier, and you might say, really? Show me. So here we go. We are going to look at the quarter circle. So if I have a shape like a quarter circle, where is the centroid of it? Well, if I want to use the formulas I just had for the xy coordinate, then what I need for x bar is to go to a location x, or y bar go to a location y, and draw either a vertical bar or a horizontal bar and let it sweep, right? So let's say, for instance, y bar. So for y bar, I have to come to this location y and then draw some small thickness dy, and that is going to be your dA element. And what is this dA, if I ask you? Well, that's the width of it times dy. And what is the width of it? On the left side, x of it is 0. On the right side, x of it is variable. It moves on this arc. So it's whatever the x of the right side is minus x of left, which is 0, times dA. So it's the x of this point. And what is x on this curve? Well, here it's a portion of an arc of a circle, and center of it is at origin. So the equation for this curve is x squared plus y squared equals r squared, right? Because the radius is r. So if I want the x of the right side, I have to get x, solve for x from this equation. So this is going to be square root of r squared minus y squared. And since x is positive, minus 0, which is x of the left side, I don't write it, times what? Times dy. This is the dA. So I have to calculate the integral of that. So when I say y bar is integral of y dA over a, in the numerator, I have integral of y times square root of r squared minus y squared dy over a. And you see here, I have to deal with this beautiful integral, for which I have to change variables and call this u, and the rest of it is like du, and then I can do it, right? But instead of doing that, it's better to use our theta coordinate. Well, how come? The reason is, while the x and y are completely variable on this curve, you see that x depends on y in this square root manner, or y depends on x in this square root manner. For this kind of boundary that you have, for this boundary of a circle, there is one thing special, and the special thing is it's r. Okay, on this curve, r is constant, it's only theta that is changing. So if you look at that element that you had, which was like a cake, slice of cake or something, when this element wants to sweep this range, all it needs to do is to change from r of 0 all the way to r of this one, this r. So from this radius to all the way to the end of it, and all you need for theta is to change from 0 to 90 degrees. You need to sweep a 90-degree angle, and radius goes from 0 to this r there. And that's all you need to do. So if I use the formula that I just showed you, what was it? Remember, it is integral of y, and y was r sine theta, and dA was r dr d theta. So you're going to get r squared dr on this side, and here is going to be sine theta d theta. And the area was just r dr and then integral of d theta. Okay, just what I showed you here. So what are the limits here? The limit, as I said, for theta, it goes from 0 to pi over 2, or 90 degrees. make sure you use pi over 2. Don't use 90 degrees because this here is integral of d theta is going to be theta. You don't want to subtract 90 from 0. You have to subtract pi over 2 from 0. And r goes from 0 to the radius circle r. Well, what would you get? This is r going to be r cubed over 3. So you simply get r cubed over 3. And integral of sine theta is negative cosine theta, right? So negative cosine theta at pi over 2, then minus 0. So you're simply going to get a 1, because negative of cosine pi over 2 is 0. Negative of cosine 0 is going to be positive 1. Integral of r dr is going to be r squared over 2. And integral of d theta is going to be theta. So you simply get pi over 2. And if you simplify 2 r's, and then this is going to be 4 over 4 times r, and then 3 times pi. That's exactly what you have here. That is the y bar of the centroid. Now you might say, for x bar of it, I have to redo this, but with this integral. And I say you don't even need to do that. Why? Because as I just told you, this shape has a symmetry axis. And the symmetry axis of this is this line that divides this angle into 2. So this is the line y equal x. That is exactly cutting this shape into 2 pieces. So if y bar is this value, then x bar clearly should be what? The same value, because it lies on this line. So you find one of them, the other one is obvious. Okay, done. So you see how much easier it is to do a simple integral with simple limits for this quarter circle as opposed to doing that square root thing that I just showed you and changing variables. So for certain shapes that are basically related to arcs and circles, using polar coordinate is always a lot easier than xy coordinate. Okay, let's move on to the next topic, which is centroid of composite areas. So if you look at the end of your statics book or dynamics or any other book, there are always these tables of different shapes that they have well-known shapes like square, rectangle, triangle, circle, trapezoid, and so on. And they show you the centroid location for well-known shapes. Here, I just did a simple Google search and you can see they're all over the place, okay? So for well-known shapes, you can find the centroids of them all over the place, right? And this 4r over 3 pi is what we just derived. But you can see it for all sorts of different shapes, okay? So now if your shape is made of a combination of these well-known shapes, to find the centroid of it, I don't need to do any integration anymore. I can simply break it down into a combination of those well-known shapes, and I can use this simple summation formula as opposed to integration, and I do it. So here, each AI is the area of one of those well-known shapes, and x bar I or y bar I is the centroid for that well-known shape. And n is the number of shapes, primitive shapes, using which I could make my actual area. So I can easily do an integration. Instead of integration of doing this, I do a summation because I have a limited number of shapes as opposed to an infinite number of these small dA elements. I have a limited number of AI elements. So I'm going to use this two simple, what we call weighted average formula. So for instance, if I give you this shape here and I say, where is the centroid of this shape shaded in blue? Then clearly you can see that I can break this shape. By the way, the 1 here is this offset here, and then 2, 3, and 3 are these heights. So I break this shape down to a triangle like this, and then a rectangle like that, and then a hollow circle. So I call them shape A1, shape A2, and this hollow one, I call it A3. And I need to calculate their A's, and I need to calculate the location of their centroids. That's all I need to do. So one thing that is very common in books is they form a table like this, and then in that table you have I, you have AI, you have X bar I, and Y bar I. And I goes 1, 2, 3. And then they fill this table and then they plug in the numbers. Now for rectangle, it's very easy. It's in the center. So we have to calculate the A of it. Look, the width of it is 3. The height of it is 2. So the area for the rectangle is 3 times 2. That is 6. And the center, if you look at the X and Y of it, you have to measure everything from the origin, not from the boundary of the shape. So the X of it is this distance. And so that is half of this 3, which is 1.5, plus 1, that is 2.5, correct? So the X of it is 2.5. And the Y bar of it is half of 2. The height is 2, so half of it is 1. That's it. Remember here, the right side is entirely 3, so for a triangle, that is just 1. For the triangle, this is your triangle. And in general, if your triangle has this total width of W and the total height of H, the centroid is here. And where is that? Well, it's 1/3 of W from the base, so it's this much. That is W over 3. And also 1/3 of the height from also the base, the other base, which is this one, so that is H over 3. So this is easily can be seen in these shapes that I showed you, and you can see that here too. Okay. Now, that was for a right triangle. For a general triangle, you have to basically here do B plus 2A, but in this case, there is no A on the right side, so it's just B over 3 and H over 3. Okay, so in this case, for this triangle that's here, this is 1/3 of the whole 1, so this is just 1/3. And that 1/3 should be added to this extra 2. So 2 plus 1/3 is the Y bar. And then the X bar here, this whole thing is 3. So this distance from here to here is a 1. And this distance from here to here is 3 plus 1, which is 4. So 4 to the right, 1 unit back, so that's 3. And the area of it, the width of it is 3, the height of it is 1, so 3 times 1 divided by 2, and you get 1.5. Now for the circle, the area is pi times 1 squared, which is just pi. Let me move it a little bit this way. And then the center of it is at the center of the rectangle also. There's this exactly in the center of the rectangle, so these numbers are going to be repeated. The only thing you have to pay attention to is this circle is a hollow circle. It's a removed area, not an added area. It's not shaded, it's hollow. So when you calculate its area, you have to make sure you add a negative here. Otherwise, your calculations are all going to be wrong. Okay, so any area hollow, use a negative. So now if I want X bar is clearly A1 X bar 1 plus A2 X bar 2 plus A3 X bar 3 divided by A1 plus 2 plus 3. Remember that 3 is negative. Correct, so you are going to get these numbers, and when you simplify, you get 2.67. So it is going to be where? If you look at this shape, remember the centroid of rectangle and circle are here. The centroid of this triangle is here. So it's somewhere between these two. Remember this here from here to here was 3. Right? Or, yeah. And then this guy from here to here was 2.5. So it's somewhere between 2.5 and 3 as you expected. And when I calculate Y bar, It's very similar. So it's A1 y bar 1 plus A2 y bar 2 and A3 y bar 3 over the total A. Now, before I even give you the number, you know that it should be between these two y's. And how much is this y? It's 2.33 and this one is 1. So it should be somewhere between these two numbers. Okay, so if you get like 2.5 or you get 0.9 or something, you know somewhere you did something wrong. So let's go ahead and calculate this number. And you're going to get 1.46 with 2 decimal. And clearly, again, it's between 1 and 2.33. So you see that is the centroid here. It is going to be, basically, if I zoom in, if you connect these two with a line, really, that's another cool thing. Let me show you or tell you about it. If you connect those two centroids with a line, so one centroid was here, which was for both shapes 2 and 3, and one centroid was here. If you connect these two with a line, it's somewhere on this line. It's like those two people on the two sides of the seesaw. One is here, one is here. And the location of that, let's do it again, look at it. 1.46 for y, 2.67 for x. So remember this location is 2.5, so, and this one is 3 and that is 4, so it's somewhere here. And then 1.46, so it's going to be somewhere like there. That's the centroid of the whole shape. Now, could the centroid be falling inside this hollow circle? Yes, it might, actually. So one of the things that you have to pay attention to is the centroid of shapes are not always on the solid portion of the shape. They could very well be on the hollow portion of the shape. For instance, if the shape you have is what we call in beams, we call it a C cross-section or U cross-section, you might call. It's called a C-beam or U-beam, you might call. Where is the centroid of this guy? Well, if you calculate it, one way you can calculate it is to break it down into 3 rectangles. So one is this rectangle, one is this one, 2, one is this bottom one, 3. And this guy has a symmetry axis, so the symmetry axis is this. So clearly it's somewhere here, but the thing is the centroid of shape 1 is there, centroids of 2 and 3 are here and here. And so it's between these two, so it is going to fall here actually. That is the centroid of the whole shape, and it is clearly outside the shaded area. So not centroid of all shapes are inside of them, especially if the shape is not a convex shape like this. They might have it in their hollow areas, okay? But that's fine. So that's another thing that I wanted to tell you. And since I mentioned this, let me just tell you another thing that might be interesting. So in this case, to make it a little bit nicer, let's say for the moment that the hollow circle is not there, right? The hollow circle is not there. So you only have the trapezoid like this. And so you only have 2 shapes here, shape 1 and shape 2. So let's call this A1 and this one A2. And let's put the same dimensions back. So this guy is a 2, this one is a 3, and this is a 1. So if I say, where is the centroid on this shape, what would you do? This is what you can do even visually without even physically calculating it through that formula. You say the centroid of the rectangle is right here. The centroid of the triangle is there. Okay? As I said, you connect these two with a line. Now, where along this line it is going to fall, it is related to their areas. Because if you look here, this formula that I just showed you, these guys are weighted averages of the x bars and y bars. So you see the weights are what? What is the weight of each one? If I expand this, this is going to be like A1, if we call this whole thing A or total A, it's going to be A1 over A x1 bar plus what? A2 over A x2 bar and dot dot, correct? So you see the weight of each centroid location is the fraction of the total area that the area of that own individual shape is basically making. So if A1 is 25% of the whole area of the shape, then the weight of this guy is going to be 25%. If X2 is 50%, the area of X2 is 50% of the whole A, then the weight of X2 is going to be 50%. So shapes that have bigger areas, they will have bigger weights and is proportional to them because their denominators are all A, is proportional to their individual A's, right? Into the AI's. So in this case, what is A1? What is A2? Remember, A1 is 1 times, basically that's 1 times 3 divided by 2, that's 1.5. This guy is 2 times 3, that is 6. So you see, A2 is 6 times bigger, 4 times bigger than A1. This rectangle is 4 times bigger in area. So this ratio is like a 1 to 4. Good? So now where on this line would the centroid fall? The way you do it is you add these two together, you get 5. Total area is like 5 units, but this guy is like 1 over 5. This guy is like 4 over 5. So is that going to be 1 over 5 of this? If this is centroid 1 and this is centroid 2, or is it going to be, if you break this down into 5 pieces, so 1, 2, 3, 4, 5, where would it fall? Is that going to be on this side or this side? The answer is always closer to the bigger one, because the bigger one has a bigger weight, it has a bigger attraction. It's like 2 electric charges. The one that has bigger charge, it will attract more or repel more. So in this case, they are like attractions, so the centroid will be here exactly. That's where your centroid is going to fall. 1/4 of this, 1/5 of this distance to this, 4/5 of this to the other side. It's always closer to the bigger area or the bigger mass. Okay? So if I know the equation of that line and that location, I can easily determine this. And you can easily verify that. So this is another good technique that you can see how to get the centers of these areas, centroids of these areas. Okay, I guess we talked about this portion, so let's move on. So can we go to lower or higher dimensions or lower and higher dimension shapes? Yes. So instead of an area, you can have basically a line, and you can find the center of a line. Now, this is important in applications where you have to deal with this 1D kind of shapes. Okay? So here, if I have an arbitrary curve, y as a function of x, or z as a function of x and y. Now, it cannot be z as a function of x and y because that is a surface, but it could be a parametric curve that x, y, and z are functions of some theta, like a helix or anything. The centroid of the curve is, it can have 3 coordinates in general, or if it's a 2D, it can only have 2 coordinates. So you do a very similar thing like last time, but instead of picking a small area element, dA, and sweep the entire surface with it, like you did here, you pick a small length of the curve dl, and then you move it all over the curve so it sweeps the entire length of the curve L. And this guy is like a very, very small thing, dl, so it is right now located in position xyz, and when you move this over the curve xyz do change based on how the curve is. So here again, you calculate the moment of this element with respect to the xyz and divide them by the total length, and you are going to get the centroid of the curve. Okay, so you need to calculate these integrals. Now the question is, what is the length of a curve in general? The length of a curve in general, if the initial point is whatever, 0.0, and the final point is 0.1. This is the integral from 0.0 to 0.1 of what? And I'm writing it for a 2D curve, not for a 3D. For a 2D curve, this goes from x of 0 to x of 1 of what? Or x of beginning to x of final of what? Integral of 1 plus y prime squared dx. Okay? So it is going to go 1 plus y prime squared dx, and that is not very hard to show, because if I say, what is this dl, what would you say? What is dl here? dl, well, in general, it can have three elements, a dx, a dy, and a dz, correct? So it's a 3D curve, and this 3D curve has three components, a dx and a dy, and a dz. Now, for 2D curves that this formula applies, your dl has only a dx and a dy. There is no dz. So what is dl? Clearly, dl is square root of dx squared plus dy squared, right? Pythagorean theorem. So L, which is the integral of dl, it is going to be the integral of square root of dx squared plus dy squared. And what you do here is you factor out the dx squared under the square root and bring it out. Now the dx squared under the square root, when it comes out, you're just going to get the dx. And under the square root, this one, since it was factored out, you're going to get a 1. And that one is going to be just dy squared over dx squared, or you can write it as dy over dx, the whole thing squared. And guess what that one is? That is y prime. Right? This one is y prime squared. So it's going to be square root of 1 plus y prime squared dx. This is what? This is the length of a curve for a 2D curve. That's the formula for it that I just wrote for you. Okay? Now in 3D, can I have anything? Sure. In 3D, what you need is, you need a parametric curve, right? So let's say x, y, and z are all functions of some parameter theta in that case. So in this case, this is like x of theta, this y is y of theta, and z is z of theta, and theta is the parameter of the curve. Or if you don't like it, I know some people might say, well, they are not necessarily a function of angle, right? Let's just call it t. T is the curve parameter. So dl in 3D, dl is going to be square root of, if you use the Pythagorean theorem again, but in 3D, it's going to be dx squared plus dy squared plus dz squared. Now, as I said, these are x, y, and z are functions of t. So what is dx? Dx is going to be x prime of t, where by prime, I mean derivative of x with respect to t, and then y prime of t and z prime of t. And t here does not need to be time necessarily. It's just a curve parameter. Times dt, dt, dt. So this is going to be the square root of this one. As I said, this is going to be x prime times dt squared, then plus y prime dt squared, and plus z prime dt squared. So if you bring out the square root, then L is going to be the integral of square root and then a dt. And this goes from t of 0 to t of 1. And this is going to be x prime squared plus y prime squared plus z prime squared. So if you have these functions and you integrate, you take the derivatives, square them, and put the square root and integrate, it's just going to be all, this is just going to be some function of time. So it's going to be a simple integral, and you can get the length of the 3D curve. Okay, no difference. So now, to practice using these formulas, we are going to look at a specific curve, y equal x squared, a 2D curve. And we want to find if I have to replace this curve, this parabola, with a single point. So this is equivalent to putting all the length of this curve, whatever it is, which we're going to calculate. If we want to put it at one single point, where is that single point going to be, right? What is the y bar of it? What is the x bar of it. We're going to squeeze the entire length of that curve in that simple point, and the location of it is what we need to find. Of course, we also need to find the total length of the curve as well, because that's the denominator of these formulas that we just had, right? We need to find it. So let's go ahead and find it first. L, using the formula I just showed you, L is square root of 1 plus y prime squared dx. And clearly goes from x of beginning, which is 0, to x of end, which is 1. So it goes from 0 to 1. Now, what is y prime? Since y is x squared, y prime is clearly 2x. So it is going to be integral from 0 to 1 of square root of 1 plus 2x, the whole thing squared. Okay, so this is going to be like 1 plus 4x squared. And calculating this integral, as you know, we have to basically use the trigonometry function and change variables so we can bring it out of this integral, or we can use cosine hyperbolic function or sine hyperbolic function. Okay, so if for x we use, for instance, because you know 1 plus sine hyperbolic is cosine hyperbolic. So if for x I use sine hyperbolic of x divided by 2, then this 4x squared is just going to be sine hyperbolic squared. And then 1 plus sine hyperbolic is cosine hyperbolic squared. Under the square root, it becomes just a cosine hyperbolic. The only thing is, what is dx? Dx is the derivative of the differential of this, which is going to be cosine hyperbolic over 2. So this is going to be the integral of basically cosine hyperbolic of x times another cosine hyperbolic of x over 2. That is this portion here. This is that square root portion. And then you, of course, have to replace. So you have to see when x is 0, what is the value of that, which is 0. When it's 1, it's going to be sine hyperbolic of 1 over 2. Okay? So you can calculate that, and of course, a dx. And by changing variable, you can do the calculation of cosine hyperbolic of x. So let's get the number here. So here I use MATLAB to calculate it. So what is 1 plus 4x squared to the power 1/2, or square root from 0 to 1? It gives you this number, and of course it always gives you a symbolic number, so you have to evaluate it. And that should give you some decimal. There we go, 1.4789. That is your length of the curve. So if somebody says, what's the length of this parabola from 0 to 1? That's the length of that curve. Okay, and it has lots of applications, as you know. For instance, if you want to calculate a rope or timing belt or anything that you need to go over some specific curves or something, you can always use this formula. But what we want is the centroid of this curve, so that is L. Now we need to calculate these numerators. Okay, so integral of x, so x bar is going to be the integral of x dl over L. Now it's integral of x is x. For dl, remember this guy here, correct? This one is dl. So this is going to be square root of 1 plus basically y prime squared dx over L. So this is going to be, and for this y prime, let me directly just plug it in. So it's going to be 4x squared. So this time you have to calculate this integral, and this time you can replace under the square root with u. This rest of it is going to be related to du. So this is going to be a little bit better this time. And again, I can use MATLAB. The limits are still 0 and 1. So this time I'm going to calculate this integral, but multiplied by x. So something like that. And again, it is going to give me some number like that. I would evaluate it. There we go, 0.8484. That's your number here. And divided by that ratio. And we can get our number. So this answer divided by basically this one. So 5.7. Let's just use 3 decimals now, 0.57. Or let's use all of it, 36. This is the x bar. Similarly, y bar is integral of y dl over L. Now, what is y? Y is x squared for this guy. So this is going to be integral of x squared. dl is still the same thing over L. So you see now you have to calculate this one. Okay, and again here you can use that same trigonometry replacement. So here I'm going to do x squared this time. And I got the number, and again I can evaluate it, and I get this 0.6063. Divided by that number. And if I plug it in, you get 0.41. So the location is 0.57 and 0.41. This is the centroid of that curve. Now, one question I have for you. Do you think this point is on the curve? In other words, if I square this number, would that, or y bar, is that equal to x bar squared? Right? Well, let's see. So this number here, right? If I square it, would I get 0.41? Here. You see, I don't. Should I? No, absolutely not. Remember the same thing I said about that C channel, that the centroid can fall outside the area. The same thing applies for curves. The centroid for curves is typically not on the curve at all unless it's a line. For a line, it's on the curve, but typically for anything else, because there is some convexity or concavity, it's outside the curve. Okay, so in this case, you see y was less than, x squared was less than y. So the centroid is above a point here. So if this is the point, the centroid is like here. And of course, again, this is not a straight line. Okay, so this is for a curve. Now, finally, what about volumes and masses? So if we have the entire volume or mass, then of course the same thing repeats. This time, instead of taking a length element or an area element, you take a volume or a mass element, dV or dm. So the center of volume comes from this formula. Everything is the same. And this time your element has 3 increments. So there is a dx, right? Or in this case, that is dy. There is some dx. And there is some depth dz. Okay, so your dv element in this case is clearly dx times dy times dz, but moving that small element all over the volume and sweeping that is not easy. So we typically pick the shape of dv such that when we calculate these integrals, we can keep that other variable x or y or z constant. Okay? Now, if the object is homogeneous, means anywhere we can say that for the entire object, mass is density times volume, then dm, and then the mass of that infinitesimal element, if rho is constant, can be rho times dv. And m is rho times v. So all I need to do is to multiply this, both numerator and denominator, by a rho, And then this is going to be what? This is going to be the integral of x dm over integral of dm. And so you see that the center of mass and the center of volume are on the top of each other. If and only if what? The density of the material is constant all over the place. If the material has a unique density and the density does not change from point to point, is homogeneous, then the center of volume and center of mass, which is this formula, and then similarly here for y and z, they are going to be the same point. Okay? If not, then you have to do it differently, because in that case, then basically based on x, y, z, your rho is changing. So you have to make this rho to be a function of location, and you cannot simply simplify these rhos with each other. And that makes it a little bit harder. And the center of volume, as I said, for a flat object, if your object is a flat object, like I showed you up there, if your object is a flat object, so let's go back here. Let's look at this. If your object is a flat object, very thin object, flat object, so the thickness of it does not change over the part. So this thickness T is the same all over the part. Then you can say that dV, the volume, is equal to dA, the area, times the thickness. The same thing for volume entirely. Volume is the entire cross-section, A times thickness, T. Okay? Then when you say integral of x dV over integral dV, if you replace it here, make this a dA times T, and make this dA times T. Since T is constant, you can get rid of it, and guess what you get? You get this one. So the center of area and the center of volume, as I said, are on the top of each other, and the center of mass, if this T is also what? A constant. The only thing is, instead of being on the top surface or the bottom surface, it's going to be here in this middle plane. The centroid will fall on that middle plane. Okay, so if it's this middle plane, it is going to be on that middle plane. Okay, going back. So let's look at one example from calculating center of mass or center of volume, and this time we're going to look at a cone. So if you have a cone with radius of base r and height h, where is the centroid? And you might say, well, that looks like a triangle. If you look at it in this z direction, that looks like this, where this guy is h and that guy is r. And guess what? This guy has an axis of symmetry. So the centroid should definitely fall on the axis of symmetry. When the centroid is on the axis of symmetry, which is x-axis, what does it mean? It means the y and z of the centroid are 0 because it's on the x-axis. So before even I do these integrations, before I do these two, I know in this problem y bar and z bar has to be 0 because the centroid of this object is on the x-axis, on the axis of symmetry. So I don't even need to calculate y bar and z bar. But x bar of it, which is not 0, I have to find it. Okay, this distance from here to here, x bar, I have to find. That's not 0. And you might say, well, if you look in this z direction, this is your x-axis. And we know for a triangle, it's 1/3 from the bottom, 2/3 from the... So if this, by the way, it seems like I made a mistake here. I'm sorry, this is h, that is 2r. So it's going to be half of this, 1/3 of this h. So it's going to be here, right? It's going to be there. No, wrong. The fact that this is a revolve shape and it's not a flat shape, you'll see that it's not going to be h over 3. Okay, and I'll show you what this one is. But clearly, you cannot just compare a cone with a triangle. Although they look very similar in one direction if you look at it, but their centroid results are not the same. So how do you do it? Well, all I need is this guy here. All I need is this top integral. Now, that's all I care about, x bar. And for that, I need to calculate volume. And I need to form a dV element, a volume. And you see here, what I care about is x. So if I can find a volume element for which the x is constant, that makes the day very good for me. So what I do is I move in this x direction for arbitrary distance x, and there, remember, for if it was a triangle like this, if you look at it from the side view, you move in this x direction, and at location x, you draw that narrow rectangle that has a fixed x, and you give it a thickness dx, if it was 2D. Now, in this case, you cannot have a small rectangle like that, because if you go at distance x and cut this guy, so bring a plate and cut this guy, your section is going to be a circle. And if you move a little bit further at location dx and bring another plate and cut this guy again, you're going to get another circle, like this maybe this time. And if you connect these two circles together and shade it, the element that you will get is going to be a disk. Look. Yeah, now it's interesting. Whenever I shade this, it is cleaning it. I don't know why Microsoft Word OneNote does that, but clearly you see the element that has a fixed x in the left side and a thickness dx, that's a disk. So your dV element should be a disk like this. Okay? Or in this case, actually, it's the other way around. It is like this, actually. The first, it's like this. This is your element, where this height of it is dx, and this radius of it r, that is variable, that depends on the location x. Because if you move this disk all the way to the left, you come here, the radius of it is almost 0. If you move it all the way to the right, it ultimately becomes capital R. Okay? So the radius of this disk depends on where you are. It's a function of this x. It's really a function. And let me not use capital R. Let me use a small r. The radius of this disk is a function of what? Location. Now, what's the volume of this? What is dV? What's the volume of this disk? Well, the volume of this disk is, for a disk, you know, the volume is the surface area times the height. Surface area is clearly r squared, and the thickness is dx, so that is the volume. Again, remember this r is a function of x, and we have to find that. But this is your volume of the infinitesimal element. Now, how much is it? So if I look at this in this side view, I'm going to see something like that, where this dimension here is r, from here to here, this is r. This dimension is capital R. This whole height is small h. And this distance from here to here is x. Yes? So with that in mind, let me in this. How much is r? Well, I can just use similar triangles. All I need to do is to look at this triangle, this small one, and this bigger one. If I look at those, we have two similar triangles. Let me draw it again here. This is r, this is r, this whole thing is h, and this thing is x. And clearly, you know that x over h is r over r. If I solve for small r, clearly you see that the small r is what? It's capital R over h times x. And it should be a linear function of position. Why? Because when x is 0, r is 0 at this side, and when x goes to the big H, then it's big R on this side. So it is. So let's go back and plug it in. So this is going to be r over h times x, the whole thing squared dx. That is your dv. And remember, the only thing I need to calculate is x bar. So x bar is integral of x dv over integral of dv. So it is going to be integral of x times whatever we have over there and x goes from what to what? It goes from the left side x of 0 to the right side, which is h. And we can calculate that. Now, pay attention, the bottom of it is the volume of a cone. And what is that? Integral of x squared is x cubed over 3. So the denominator is going to be h cubed over 3. 1h of it will be simplified. Or actually, this is power 2. So 2 of the h's will be simplified. And you get r squared. So you're going to get h, correct? You're going to get h, 1h, and then r squared over 3. And this is what? This is the volume of a cone. It's this cross section, right? And pi r squared over h. And you might say, where did the pi go? Yeah, we made some small mistake. Where was it? Here. That was the small mistake. It's pi r squared times dx. Okay, this is the basically cross section of this disk. The cross section of this disk is pi r squared times dx. So here you should add a pi, and you should add a pi here and here. There is a pi that we missed, pi r squared dx, not just r squared dx. So it's going to be pi hr squared over 3. Clearly, this is the cross section of the base of it times the height over 3. And we always say the volume of a cone is 1/3 of a similar cylinder. And you can see that. And if you look at the top one, now the pi's will be canceled ultimately. But if you look at that, this here is x squared times x is x cubed. So you're going to get x over 4 over 4. So you're going to get h to the 4. And this is h squared. So you're going to get h squared over 4 r squared. So you're going to get pi h squared and then r squared and then over 4. And if you simplify everything here, you should get 3h over 4. And this is where the centroid is 3h over 4. Now, where is that? If I clean this up and look at it, it says if this is h, break it into 4 equal parts. It's 3/4 from the end, 1/4 from the base. So this here, from here to here, is only h over 4. Not h over 3, it's h over 4. This is where the centroid is. You see, for a triangle, it was 1/3 of the height. For a cone, is 1/4 of the height. Okay? So clearly you see that you cannot compare a cone to a triangle because of this revolution that you don't have in the triangle. And that is the location of the centroid for a cone. And again, if you go to those websites and you just look at the well-known shapes, but instead of 2D shapes, you look at 3D shapes, you'll see for the cone, this number is reported. Okay, so this was an example of calculating the center of volume or center of mass. The last question. I know this video is getting long, but I wanted to tell you everything you need to know about centroids. Is there any way you can find the centroid of a shape basically with experiment, right? So if I give you a shape, if I have an object that is already existing, so I just grab some shape like this, just like this guy, and it doesn't have well-defined boundaries, well-known functions that you can do y of the top minus y of the bottom, x of the left minus x of the right, or anything like that. If I just give you a slab like that and say, hey, where's the centroid of this crazy object, or a cylinder block or anything, how would you do that? Well, depends. There are several ways that I just want to briefly talk about them. So if the object is a narrow, slender object, like for instance, you have like a 2D object, for instance, let's say it's a key or something. So I have a key, right? Something like that. And I say, where's the centroid of this guy? The best way to do it is to basically balance it on a point. So just like the seesaw, I bring it and then I put this key sideways, so the key is kind of like this. And then I move this support point until I see the two sides are balancing out and this guy stays stable and doesn't tilt either way. Then that point should be my centroid. Okay, so if it's a thin, simple object that I can balance it on one point, that's the simplest way to do it. Now, if it's a bulky object and it's not easy to balance it on a single point, like an engine block or anything like that, then if you can hang it from 3 points. So let's say I have this kind of crazy shape object. What I can do is I'm going to hang it from 3 points. So first I pick any point on the boundary, doesn't matter, and then I hang it from somewhere and let it finally stable, let it stop all the tilting and all the oscillations and go stable. When it goes stable and doesn't tilt and doesn't oscillate anymore, I know that the centroid should be right below this line of this rope or chain. Because if it is not, if it's here or here, then it is going to create a moment, because there is a distance from the mg force to what? To the axis of hanging. And this mg times that distance will create a moment, so it either tilt this way or tilt this way. So the centroid should definitely be on this line. So what I'll do is I'm going to go ahead and I draw this line on the object, and I know my centroid should be somewhere on that. Then what I will do is I go ahead and redo the same thing, right? But this time I hang it from another point. So I repeat the same experiment. And this time, let's see if I can use the tools of Microsoft OneNote and do something nice. So if I copy this here, this time I'm gonna rotate it. And I'm going to basically, as I said, hang it from another point. So this time I'm going to pick another point here and I hang it from there. And again, let this do all the oscillations and come to stability. And if it stays like this, then I know again mg should be on this line, because otherwise it will tilt. And that line and this line will intersect. This is where the centroid is. Now, if you need the 3D, you have to hang it from another point, maybe in the depth direction or something, right? Maybe this time here. That should give you another point. And these 3 lines, if you can draw them, they should pass through the centroid of the object. Now, the problem is not always you can draw these 3 lines. Why not? Because some of these lines will pass through the inside of the object. Okay, like this line, if you continue that, it passes through inside of, and I cannot continue these lines through inside of the object. I cannot draw them. If it's a simple 2D object, yes, I can draw it on the surface of it, assuming that the surface is flat. But if it's 3D, there is no way I can draw these 3 lines. So what would you do? If it's a complicated 3D shape, then the best way to do is a 3D scanner. So I use a 3D scanner, and then I basically scan this shape. So what? When you have that, now you can convert the point cloud that you get from the scanner, and you can convert it. So first you get the point cloud, and then you convert that point cloud into a solid model. In what? In a CAD software like SolidWorks or CATIA or anything else. And then in CATIA or SolidWorks, there are options that can directly give you the location of the centroid. You can exactly calculate the location of the centroid, which is done by all small elements. So in a CAD software, you can do that. And I mentioned it in my CAD videos, how to do it. Now, is there any caveat for this scenario? Yes. What is that? The cavity, if there is any cavity inside the object that the scanner cannot scan, those cannot be modeled in the CAD. So CAD will give you the centroid assuming that the object is entirely solid. If there is any cavity inside the object, even CAD cannot do it. So you have to have a way to model those cavities so CAD can give you a relatively good location. Okay, so in general, if you have a shape that is just already made and you have no idea the functions for the surface of it or anything, finding the centroid even experimentally could be a challenge. So all the things that here we have done, we assume that we know all the functions and we can perform those integrations. So hopefully this long video, which is more than 1.5 hours, is useful to you. I covered everything I should have covered about the centroids, whether area, volume, composite areas, curves, polar coordinates, experimental determination of centroid, and everything. So hopefully this video is all you need to know about centroids. Thank you so much.